So in this video, we are going to talk about dictionaries and vertices. We are going to make formal the connection between dictionaries and vertices of the feasible region. Okay, and that's going to give us the geometric view of what simplex is up to. All right. So what's the main message of this video? The main message of this video is that dictionaries of simplex correspond to the vertices of the feasible region. What that means is every dictionary DI is associated with a vertex. All right. Every dictionary DI is associated with a vertex of the feasible region. And likewise, we will see that every vertex is associated with a set of dictionaries. Okay, with a set of dictionaries. If the vertex corresponds to a non-degenerate dictionary, it will be associated with a unique one. If it corresponds to degenerate, it could be associated with multiple dictionaries. It may be associated with multiple dictionaries. And we will see this correspondence. We will leave aside the question of degeneracy in this video in general. When I talk about dictionaries, you may assume that they are non-degenerate. If I happen to discuss degeneracy, I will discuss it separately. I will mention that I'm talking about degenerate. Otherwise, assume that I'm talking about non-degenerate vertices. Because when you get to degeneracy, there are many exceptions to what I'm going to say. All right. So with that in mind, let's get forward. All right. So here is our favorite linear programming problem once again. Okay. And let me, without much further ado, take this problem and look at a dictionary of this problem. In this dictionary, x4 and x3, which are the slack variables corresponding to this constraint and this constraint, the first two constraints. Okay. All right. So those two are going to be non-basic. And the other four, x1, x2, x5, and x6 are going to be basic. All right. So let us interpret this dictionary as a vertex. Okay, I would like you to interpret this dictionary as a vertex. So to do so, I'm going to hide the parts of the dictionary that absolutely do not matter to me. So I'm going to hide almost everything in the dictionary. So gone. Okay, we just need to know two things. What two variables are going to be non-basic? So here x3 and x4 are non-basic. All right, that's all I need to know. Let me now go back and geometrically interpret this. What is x3? x3 is going to be this constraint. All right, and the dictionary says let's set x3 to 0. That's what the dictionary is telling you. x4 is going to be this constraint, and the dictionary says x4 equals 0. So what does this mean? So we are setting slack equals 0. So when we set slack equals 0, what does it mean about the constraint? Okay, so if you have thought about it, okay, slack equals 0 means that the constraint is active. All right, so slack equals 0 means that the constraint that we are talking about is actually going to be active. Okay, so in that case, the constraint corresponding to x2 less than equal to 11, which is x4 equals 0, and the constraint corresponding to minus 3x1 plus x2 less than equal to 2 are both active. So active and active. And that's what the dictionary is telling us. So the dictionary has set two non-basic variables to 0. Why 2? Because 2 is the number of variables in the original problem, the dimensionality of the original problem. And going back to the original problem, we can interpret it as saying two slack variables are 0. If two slack variables are 0, the corresponding constraints are activated. Therefore, a dictionary like this activates two constraints. Right? Second thing, if we go back for a second, I'll bring back the numbers. We see that the dictionary is feasible. Okay? So the solution that was represented by the dictionary, the solution that was represented by this dictionary, whatever it was feasible. Okay? The solution is feasible, and it activates two constraints in the original problem. Which means that if I just restricted myself to x1 and x2, don't worry about the slack variables because they increase the dimensionality to 6 dimensions, and we want to study the 2-dimensional problem. So bringing things back to the original problem before we added the slack variables, we now conclude that the solution that's associated with this dictionary, focusing on x1 and x2, okay, let me bring back things. Okay, the solution that's associated with this dictionary, 3,11, saturates or activates two inequalities. And if it does so, it's going to be a vertex. Okay, it's feasible, activates two inequalities. And I haven't convinced you that the rank of the activated inequalities is 2. But let me do the convincing a little bit indirectly. So if the rank weren't 2, then what would happen is we wouldn't get this point 3, 11. All right, so we wouldn't get this 3, 11. So the very fact that you can construct this dictionary, we can prove that the rank of these two saturated constraints, x4 and x3, implies that the two activated constraints in the original problem have rank equal to. So therefore, it's a vertex. So hopefully you have gone through the reasoning, the chain of reasoning that I have mentioned so far in the last 2 minutes to convince yourself that this dictionary represents a vertex because it is feasible, number one. Number two, because it activates two inequalities in the original problem by setting two slack variables to 0, and the corresponding inequalities in the original problem get activated. And number three, the rank is going to be 2. And that argument comes from the fact that you can make this dictionary and you can fix, thanks to this dictionary, x3, x1 and x2, the original problem variables to 3 and 11 uniquely. And because of that fact, the rank of the inequalities that you fix, activate, must be equal to 2. All right. So if that's clear, let's move on to one more. Okay. Let's move on to this dictionary with x2 and x5 being the non-basic variables. And that's all I am looking at so far. So what it's saying is x2 equals 0 and x5 equals 0. All right. So what does x2 equals 0 activate? So x2 equals 0 activates the constraint x2 greater than equal to 0. Remember, that's even though in the standard form we assume it as a constraint, it's still a constraint in the original problem, and it still contributes a phase. It contributes this phase, everything above it. So geometrically, it is still a very meaningful constraint, and therefore x2 equals 0 can be said to activate x2 greater than equal to 0. x5 equals 0 can be said to activate, okay, can be said to activate what? Can be said to activate this constraint, x1 minus x2 less than equal to 3. So therefore, you have x2 equals 0 and x5 equals 0 can be equivalently written as x1 minus x2 equals 3. These two system of constraints give us a unique point, okay, a unique point which is 3, 0. Now, why is 3, 0 this point here, right here, okay, 3, 0, a vertex? 3, 0 is a vertex because it activates two constraints in the original problem, 1 and 2. It's feasible, and number 3, the rank of the activated constraints, so 0, 1, 1 minus 1, this matrix has rank 2, which means that, geometrically speaking, the activated constraints meet at a point and define a point uniquely. And therefore, you get the fact that 3, 0 is a vertex. All right. Let's do one last example before we generalize. And this last example is this cube defined by 6 constraints. All right. And for the time being, we can forget about the objective. All right. Let's take an example of a vertex, or let's take an example of a dictionary and write down the vertex corresponding to it. So let's take a dictionary whose non-basic variables are going to be x1, x5, and x3. Okay, let's say these are going to be my non-basic variables. All right, since it's the original problem has 3 decision variables, it's got to have 3 non-basic variables, and the way we count m, we'll have 3 basic variables here. Okay, so we had 3 slack variables, x4, x5, and x6, corresponding to these constraints, x1 less than equal to 1, x2 less than equal to 1, and x3 less than equal to 1. All right, so what vertex is represented by this dictionary? Let's call it D1. Very simple. If x1 is non-basic, then x1 greater than equal to 0 is saturated. If x5 is non-basic, then x5 greater than equal to 0 is saturated. But this is a constraint in the slack form, not in the original problem. Therefore, we have to take it back to the original problem and say x2 equals 1 is saturated. Or instead of saturated, you can also say is active, is active, is active. All right, x3 activates x3 equals 0. So therefore, we get the point 0, 1, 0. That's the point which is being activated. So it's this vertex at the right-hand corner right here. That's being represented by this dictionary. So hopefully this is enough to now convince you that if you have a feasible dictionary, you need to have a feasible dictionary like this. If you can write down a feasible dictionary like this for a problem, Okay, let's put the problem in the standard form. We haven't talked about dictionaries for other forms. We have just talked about it for the standard forms, all right? Okay, so what we are saying is that the solution will make at least n constraints active. And the reason is that you have to set all of these non-basic variables, and there's n of them, xi1, xi2, xi3 to xin. All of them are becoming 0. And if this was a slack variable, then the corresponding constraint in ax less than equal to b is active. And if this was an original problem variable right here, then the corresponding constraint in x greater than equal to 0 is active. Okay, so the solution associated will make at least n constraints active. Okay, and the rank of the active constraints has to be n. We'll prove this. If necessary, I'll write down a proof in the discussion forum. Okay, and this is an interesting proof to do, that the rank of the activated constraints will be n. Okay, and therefore the solution associated with the dictionary is a vertex. That's it. So dictionaries represent vertices, and we have formally defined vertices. We know what a dictionary is. Therefore, we are now able to map dictionaries and vertices. Okay, so one last question before we move on. So we said the solution associated with the dictionary will make at least n constraints active. Can you think of a situation where the solution can make n plus 1 constraint active? Okay, so if your intuition says that this happens if one of these variables bi is 0, then you're absolutely correct. So the situation where more than n plus k constraints become active is a situation where the dictionary is degenerate. So you need a situation where the dictionary is degenerate to activate more than n constraints. And we'll talk about what are the implications of this later on. But I asked you to assume that the dictionary was not degenerate, so we will keep that assumption going until we can. All right? And whenever we are saying something, we will modify it accordingly to include degenerate cases. All right, so we are almost at the end of this segment, and what we have done here is we have defined a vertex. We have defined a vertex as a feasible point that makes at least n inequalities active, and the rank of the active inequalities is n, so that together the faces defined by the active inequalities intersect and define a unique point, which is called then the vertex. All right. We talked about feasible dictionaries in simplex, and we said the solution associated with a feasible dictionary in simplex must be a vertex of the feasible region of the polyhedron. All right? And finally, we are now ready to ask the question, what does pivoting do? What is the purpose of pivoting? What does pivoting do? Can we now interpret it geometrically? When we interpret it geometrically, we have learned a lot about how simplex actually works, and our intuition is complete. So I will see you in the next video, where we will go ahead and make this final step and make our understanding complete. Thank you.